And I've got a few questions for you guys. Does anybody use iCloud Keychain? Few, OK. And there's a really great typo on the website. Somebody wrote intercepting iCould Keychain. I thought that was really clever. I didn't think of that, though. So I've been working in security for about 15 years now, currently at a small consultancy. You can follow us on Medium. We have some contact info for there. And Sweden is actually very special for me when it comes to computer security. Because when I was 16, I kept a really normal sleep schedule, and I was really interested in hacking, which meant that when I got online, I overlapped with real Swedish hackers that didn't sleep at night. They didn't do their homework. They stayed up until like 5 a.m., which overlaps perfectly with the New York time zone for a normal teenager. And there was a website called wargames.unix.sc. Does anybody remember this? Oh, I would love to meet up with you guys. It was just like the best. People were super interested in learning how to program, learning how to code, and learning how to hack. And there's a lot of crazy stuff going on back there. Major Linux distros were being compromised every other month. It seemed like complete chaos. White hats were being hacked by black hats. It was like all this internet drama. And as a 16-year-old, I was like, wow, this is really crazy and this is really interesting. I want to learn more about this. And what was really nice about this Swedish website was they had a really friendly environment. There was no room for being a jerk, basically. So it was a great place to learn. And today I'll talk to you guys about iCloud Keychain in depth. iCloud Keychain has been around since about 2012, but there's a lot of stuff that's really not well documented. So this presentation sheds a lot of light on some of the details about how it actually works. And what is this service, iCloud Keychain? Essentially, there are two major components, secret syncing and recovery. So you can synchronize your secrets between all of your devices. And what kind of secrets am I talking about? I'm talking about credit card numbers, Wi-Fi passwords, Safari autofill, specific application passwords from different apps used that have enrolled into this. And it's done in the cloud. And as some people working in the security industry might know, cloud security sometimes is a little bit cloudy. And where exactly is iCloud anyway? It's not in the sky currently. It's a bunch of big companies that host huge data centers that are very scalable. Companies like Amazon with AWS, Google Cloud, Microsoft Azure, and of course Apple has their own servers as well. And in certain countries, for Apple to enter those markets, they were required to use that country's data centers, like in China and Russia. So Apple designed iCloud Keychain to be very secure because of the sensitivity of the information there, credit card numbers and so on. There's a lot of incentive to break in there. And also because they don't necessarily control the computers that are holding the data, because they rely on third parties to get to this Apple scale. We're talking about hundreds of millions of users. And they did this with end-to-end cryptography. Have you guys heard about end-to-end cryptography before? And we'll talk a bit about it. And it's really great for privacy because the keys to decrypt the data only live on the endpoints on those devices. And the cloud computers in this scenario only act as a conduit of the encrypted information. They don't have the keys to access that info. And that lets Apple make claims such as even if there's a rogue insider at Apple or somebody breaks into an iCloud server, iCloud Keychain is still secure. And they had a little bit more foresight than that even. They also secured Keychain even if an iCloud account is compromised. So in 2016, something like 400 million passwords got dumped from hacks over the past couple of years. A lot of passwords out there. Password use is a huge problem. So it's not that hard to break into a random iCloud account and try to monetize it. So Apple went one step further, requiring that you actually have to have a trusted device in addition to the iCloud credentials. They really tried to make it watertight. Of course, we're here at a security conference, and one of the fun things about my job is we get to celebrate failures. And we found some critical flaws that undermine this end-to-end cryptography. And it would have allowed someone to intercept those secrets anyway, despite all the measures and effort that they put into iCloud Keychain. And they really spent a lot of money if you look at some of the mechanisms they used. And what's interesting is that these flaws were in parts of the protocol that you wouldn't find in Apple's white paper that weren't well documented, although they were in open source components. And so we're going to describe some of the previous work on iCloud Keychain. Then I'll talk to you guys about how iCloud Keychain works, and I'm going to really focus on the syncing part, which has not really been documented before. And then we're going to talk about the bugs. So some of the prior work. In 2014, Andre from VIA Forensics, I think they're now called Now Secure, did some research on iCloud Keychain. And he really focused on the recovery and looked at that. And he was very suspicious of iCloud Keychain because in the recovery mechanism, by default, you have like a 6-digit PIN code, right? So you can brute force that pretty easily. However, there's some more things in there preventing brute force that we'll talk about. He also found a great bug reported in 2015. And then last year at Black Hat, Apple went into more detail than they had before about a lot of different iOS security features. So if you really want to get your head around iCloud Keychain, check out this presentation as well. There they'll explain how they set up their HSM, and they use a one-way hashing function, also known as a blender, for the private keys for their HSMs. And earlier this year, the CEO of Elcomsoft, have you guys heard of Elcomsoft? They're a leader in forensics, did a presentation on iCloud Keychain. And he questioned whether or not the two-factor authentication could be weakening the protocol. So they didn't find a solid break, but they implied that there might be something there. So that's another interesting one. And of course, you have the white paper. And the white paper has a lot of explanations about how some things work, but when it comes to the level of detail that I would want, or a security researcher that wants to test if a protocol is really secure, the white paper doesn't have that level of detail. It's just like acronyms and names of protocols and kind of a very high-level view. But the actual protocol, how does it really work? You're not going to find that in there, unfortunately. And when it comes to crypto, it's really great to know how a cryptanalyst thinks. So this is a picture of Robert Morris Sr. His son, Robert Morris Jr., is infamous for the Morris worm. And besides having an excellent beard, Robert Morris Sr. was a cryptanalyst at the NSA. And he says you should never underestimate the attention, risk, money, and time that an opponent will put into reading traffic. So if you're building crypto, you have to be very paranoid because you're dealing with people like Robert Morris Sr. that will do whatever it takes to get your secrets. So iCloud Keychain has two aspects to it. One part is the recovery. So what happens if you lose your iPhone, you lose your Mac, it's all gone, but you had a password there in autofill that you have no way of getting. That would be a pretty terrible experience because you could end up getting locked out of all your accounts. So iCloud Keychain lets you actually recover all this information without needing any of those devices. Now, we'll talk about that in more detail, but a feature like this tends to be very much at odds with end-to-end encryption because you're supposed to need one of those devices to get that data. So there are some interesting mechanisms there to make this secure. And then it's syncing. So as you're updating secrets on your Mac, they show up on your iPhone or your iPad. And that's the second feature for this service. And recovery, a lot of it hinges on this hardware security module-based escrow system. So to prevent brute force attacks, Apple has specialized hardware in all of their data centers that interact with iCloud Keychain. And this specialized hardware prevents brute force attacks because in there they have hardware counters that limit the number of attempts that can happen. So it's, I don't remember the exact use, but something like after 20 attempts, the data will be wiped and it's gone and the secrets are lost forever. Another thing is SMS verification. So we know SMS isn't the most secure thing. We know nation-state actors target SIM card manufacturers and telcos, but it does certainly increase attacker cost. And you also need additional passwords. So separate from the iCloud password, when you set up iCloud Keychain, you get something called an iCloud security code. It's an additional password that's needed for this. If you're using two-factor, it's a little bit different, and instead you need one of your other device's passcodes. And you might think, okay, well, that's a little bit risky because you're still sending your password, so what's to prevent a man in the middle during the recovery process? Because that's hard to do correctly. Well, Apple also uses something known as Secure Remote Protocol. It uses some modular exponentiation and hashing, sort of like Elgamal, not exactly that, to do a proof of work, sort of like a zero-knowledge proof, that you know the password, that that is in this escrow system, but you'd never reveal to the server what that password is. And actually, the server doesn't have the password or even the direct hash of the password, so they can't brute force the password either using some nice math. So it seems pretty good. And let's see. Some issues here with the. Okay, so the syncing part. Secrets are being constantly synced between the different devices. And this is what I'm going to focus on and go into detail that people haven't really gone into detail about before. There's end-to-end encryption when the syncing happens. So it communicates to the iCloud systems, but what it's communicating is actually encrypted data. Apple doesn't have the keys to that data. The keys are generated on the devices, and they never leave the devices. And having a little trouble with Wi-Fi in here. To do this, devices establish a circle of trust. And this circle of trust is what controls who can enter this secret syncing. And in order to join the circle, you need approval from one of the devices that's already in the circle, or you go through the recovery mechanisms, which requires those passcodes and the SMS and so on. And the protocols involved with the syncing, there are two major ones. So there's one that I'll call SOS circle. This is not like something you'll find in RFC, but it's a protocol that Apple has developed in their code as a framework for establishing a circle of trust between different devices. And Keychain Sync happens to be one of the applications. And the second part of that is the off-the-record protocol. Have you guys heard of off-the-record? We had the fortune of getting a response from Ian Goldberg, one of the authors, and he was surprised to find out OTR was being used here. And if you check out that white paper and you look up off-the-record OTR, you won't find those words in there. So we're pretty surprised to see this in Apple's code. First, a run through what SOS circle does. So there's a signed syncing circle. So it's a blob of data being stored in iCloud, and it's signed by each of the devices that have been trusted. And in order to join this, you need that iCloud credential, the password, and then one of these devices would have to approve it, or you go through the recovery path using those mechanisms. And the math that this really hinges on is 256-bit ECDSA using a NIST curve, SecP256R1. Bitcoin uses SecP256K1. And this is one that has some constants that very paranoid cryptographers like DJB question. But if you're worried about this curve being used in iCloud Keychain, you should probably be more worried that it's used in TLS all over the place. So kind of a high-level overview, as explained in the white paper. When this blob is created, it includes information about all the different peers. So it's got information about the device type, the version of the protocol it's on, and then the public key from that device that was generated on that device. The private key, of course, never leaves the device, but the public key is there, and the peer info is signed by that device. And then the whole blob is signed by the device as well. And then there's an interesting addition here, which really ties in where the user interaction is needed. The iCloud password at the time is used to derive another elliptic key that also signs the circle. So you need the interaction and you need the password as well to join the circle. So when a second device wants to join, they create an application ticket that has the peer info again. It will have the public key of the identity of that device, and it will be signed by that. And again, with the password with the key derived from the password. When the first device approves, we'll add the peer info in and sign it. And then something called countersigning happens. And in countersigning, if a device sees that a device that they trusted has signed the circle, they'll stamp their signature on as well. This is to help facilitate the syncing between all of the different devices in a seamless way. So now when you have a third device that comes in, any of the devices can now approve it. And automatically, the other devices will sign it. So this seems pretty okay, but when you start thinking about usability, you might see that there's some issues here. For example, what happens if you're on the road at a conference, you lose your phone, you didn't have your computer with you, and you want to go recover your stuff, you buy a new phone real quick, you go to recover it, what happens to your other devices? Would they be booted out or not? With what I've just described, it has to be signed by another one of the devices, so it would imply that you would boot out the others. But if you go and try this, that's not exactly what happens. And I'll explain what's actually going on in a minute. And I know there's like all these codes and passwords and things going around, so here's a chart that explains the different modes of operations. So there's a bit of a difference between having two-factor on your phone and not having it. Without two-factor to join, you just need the Apple ID password on the device that's requesting to join, and then the other device just approves it and says, yep, it's okay, I trust this device, and you enter the password again. And to join without it, you go through the recovery path, more or less. That's where you need the SMS code and the iCloud security code, which is something that was set up when you rolled in iCloud. And this lets you restore to a device without approval from somewhere. And again, it depends on that escrow system being secure. The second path is if you do have two-factor enabled, you need to go through the 2FA approval steps. And the iCloud security code is swapped by one of the existing device passcodes. If you look here, there must be something else going on to recover without booting the other devices, because the identity keys don't leave the devices, but it has to be signed there. So we dug into exactly what's going on. And here's some information for the documentation where they spell out the attributes that are set on the keychain. So set this device only. They don't get backed up to iCloud backup. They don't go to iTunes backup. They stay on the device. They don't leave. So it turns out that there's a hidden peer. That's also not in the white paper. And when a circle is first established, this cloud peer also gets added in there. And it has an attribute set for KSec synchronizable. So if you're an iOS developer, this is the keychain attribute that you set to get your password into iCloud Keychain. So the private key for this cloud peer ends up in iCloud Keychain itself. So that implies that you can get it through the recovery mechanism. So this is what the signed syncing circle actually looks like in a more accurate portrayal than spelled out in the white paper. When a device is first set up, there's also this cloud peer that's there, and it's called out as a hidden peer in the code. And then if you have two devices, you have the two devices, and then the cloud peer is shared. There's no like new cloud peer for each additional device. It's just shared across all of them. And as a security researcher, you get really excited when you find undocumented stuff that shouldn't be there. There might be some protocol breaks, because it seems pretty tricky to do this correctly. And like, where is this private key going to be backed up? It's already in the cloud. It seems a little bit tricky, but it's mostly okay as far as I could tell. But you can take a look and see if you can find some issues there. I don't believe it's in the iCloud Backup Keybegs, but even if it were, the keychains, when they get backed up to iCloud backup, can only be restored to the device they originated from, because they do key wrapping with an AS key that's embedded into iPhones. So they should be okay. Maybe from the Mac side, there might be an interesting angle. And then it's really this keychain escrow for recovery, where you can get the private key. And that's how it's possible to join a circle without booting out the other devices, which I think is a pretty important protocol detail to understand when looking at keychain syncing. All right, now the OTR part. So OTR is what provides that end-to-end encryption. And the circle part is what establishes that circle of trust. And they do tie in together. So OTR provides forward secrecy. If someone is observing traffic and later on they get into the device, they can't go look at that past traffic and decrypt the data. It also has some degree of deniability, which is not so relevant for iCloud Keychain. And OTR does Diffie-Hellman with ephemeral keys, and then these persistent identity keys are what's used to verify the peers, and those identity keys come from the signed syncing circle. And the encryption is 128-bit AES in counter mode, and OTR even rotates keys to make things like side channel attacks a lot more difficult to pull off. And so those were the protocols in an abstract sense, but where is this actually transmitted? So devices talk to iCloud through at least two services, one of which is called key value store. It's just a big lookup table. you get about 10 megabytes of data that you can arbitrarily store here. And one of the attributes is reserved specifically for iCloud Keychain, and something third-party apps can't access or modify. And it's this end-to-end encryption that lets Apple claim that they can't access the data. And what does the OTR key exchange look like? So they set up some Diffie-Hellman, and the pure identity keys from the SOS circle are what's used to verify that those parameters came from somebody that was trusted. So if there's a man-in-the-middle attacker in there, they can initiate a Diffie-Hellman key negotiation, but they don't have the pure identity keys to sign those parameters. So they can't prove that they're trusted, and they would be booted out and ignored. So the security of OTR really hinges on this key exchange process and that signature verification. And once this secure channel is set up, that's where the plaintext password material, the credit card numbers, Wi-Fi passwords are transmitted. There's nothing else beyond that. And one of the things about OTR is that it doesn't have a group chat encryption. So actually, iCloud Keychain does a Fanout pair-out negotiation, which is a little bit noisy, but performance isn't so important for password credentials because they don't change very often. So you wouldn't necessarily want to use OTR for group chat, but it's fine for this use case. And quick recap of Apple's security goals. So with what we've talked about, this is how they're able to achieve these things. So if someone breaks into iCloud, there's a rogue insider. You need these identity keys to set up the OTR exchange. So it keeps people out. If you break into an iCloud account and you can start negotiating data on the key value store, again, you need those identity keys, the private keys, to actually do a key exchange to get the secrets. And there are really multiple layers of security. First of all, you have TLS, all on the outside, and the communications to iCloud. Then you have the security of the servers themselves, iCloud, and they have all kinds of compliance regulations. It's pretty heavy-duty stuff. You can't just walk into there and pull some drives. And then you have the end-to-end encryption, which is achieved through SOS circle and OTR. So if you're an attacker and you want to break into this, what are your options? So the most direct path is find some exploit, send somebody a remote jailbreak like the Pegasus exploit, and just break into the phone, and then you get all the passwords. That's the most direct route. The second route is to try to attack this protocol itself. And to defeat the protocol, you really got to get past two steps. So the first layer is this outer layer with the TLS, or getting access to the iCloud account, or getting into the Apple servers. But even if you've done that, now you have the end-to-end encryption that's stopping you. So you got to find a flaw either with the SOS circle mechanism, or you got to find a flaw with the OTR to actually break in. And the flaws we found were with the OTR. So there was a very severe cryptographic problem with the signature verification. We also found memory corruption that could have led to remote code execution. And a lot of both these issues were exacerbated by the fact that there's been no TLS key pinning on the iCloud communications. And that's something that was brought up back in 2014, but Apple still hasn't addressed yet. So this is where the crypto failure was. And it was very similar to Goto fail. Do you guys remember Goto fail? Like Goto fail repeated twice. And semantically, this bug is actually identical. And even more interesting is when that bug came out, this used to be in the same code project. So people running static analysis tools, they failed to find this bug. And we'll go through the code real quick. See if you can spot it while I'm talking. So this is a function called SecVerify signature in Mac. And it's responsible for going through, extracting the signature off the wire from the packet, and then crunching some numbers, running the math, and seeing if the signature on the parameters adds up, and they are who they say they are. It returns a result code saying whether or not the signature was correct, and it also sets up the Diffie-Hellman key. So on this line, they reset the result code to success when it just extracts a few 4 bytes off the wire. Now, if something goes wrong, they have to reset this result code and say that something went wrong. Otherwise, it could fail quite horribly, like on this line, where it just it goes to the exit routine with the error code still remaining as successful without actually doing the signature check. It just bypasses it completely. This is a really like terrible way to write C code with macros like this. You really shouldn't do anything like this anywhere near crypto. And it's quite trivial, and it lets you bypass the signature verification completely. When we were verifying this looks a lot like bug doors, you know, so it was kind of fun. And our trigger, the smallest trigger we could make was about 32 bytes for fooling the signature check. You can see it in the bottom left there, some base 64 with the OTR message. So something like this would come across the wire after sending the initial Diffie-Hellman messages. And this would just bypass the signature check. And then someone could start negotiating secrets. And if you think about OTR, because it's an ephemeral key exchange, this is all you need to get into that channel. The long-term identity keys that stick on the device, you don't need those at all. And this attack is also silent. There's no kind of user notification. If you look up the signed syncing circle, there's been no modification there. And it's also 100% reliable. So it's a great bug if you're a rogue attacker on an Apple server. And this really undermined a lot of their end-to-end encryption goals, which are sort of important. We also found an additional flaw with the way they're handling stack memory. If you sent a packet with a very large size, it would overlap into the stack of an adjacent thread. And since we reported this, there's some great research by Qualys where they really talk about this bug class. So if you're into C, definitely look that up to learn about stack clash vulnerabilities. And this could have led to sandbox escape from one app into SecD. Again, that's where all the keychain secrets are. So pretty good daemon to break into on iOS. It's remotely triggerable. It is very tricky to exploit, though, because you're racing between hitting the guard page between the two stacks and the adjacent thread actually activating the stack frame you corrupted. This category of bugs is definitely exploitable, but not in a reliable fashion. We'll wrap up real quick. It's actually quite exciting to see end-to-end encryption used by a very large company because it's one of the best ways to have privacy for people. And it's quite bold, I think, to have end-to-end encryption because it's also an easy way to lock people out of their data. And we covered the Keychain Sync protocol and the OTR flaw. Reflecting on the security industry, I think this should have really been found after Goto fail. So all the people that invested in static analysis tools around that time, thinking we should catch the easy bugs, they should have probably caught this one. Because semantically, it's very, very similar. I don't think you can find it with grep. You need to do actual static analysis. Another thing that I would say is I think we need a lot more transparency into how protocols work. So some companies are trying their best. They publish white papers that actually go into protocol details, and that's great. I think Apple maybe didn't deliver on the transparency here because there's a lot of info in that white paper. But it would be nice if companies published very detailed protocols when they roll their own crypto. And if you're really interested in iCloud Keychain, I would encourage you to check out some of the stuff that Elcomsoft is talking about. I think the two-factor implementation needs a little bit more research. Some of the details in there are also not very well documented. So if I were to spend more time on this, this is the first place I would look. Thank you.